Hello everyone. We have been talking about projection operators in the last video. So as a reminder, we defined the projection operator in the following way, and we saw that if I have any vector psi, then this projection operator projects the component of psi in this v direction. This is the new vector, and this is why it's called a projection operator, but it has some properties that we also verified. One of them is this pi square is equal to pi, because if you take the projection once in that direction, no matter how many times more you take it, it will give you the same result. That is why you have this pi square is equal to pi. All right, and then if you want to project into two orthogonal directions, then that would give you 0, right? Because once you take the projection in one direction, any projection in the orthogonal to this direction would give you 0. All right, so these are the properties that we saw in the last video. But there was one thing to notice, is that we were projecting any vector psi in a one-dimensional space V, in a one-dimensional subspace V, right? By subspace, I mean a smaller part of the vector space, but it within itself is a vector space, right? If you remember the definition of subspace. So what I'm trying to say is projection operators doesn't necessarily have to be a one-dimensional projection operator, because this is a one-dimensional projection operator, but in general it doesn't have to be like that. All right, so let's see how does that work. So again, we will work out with an example. So let's say that we have like something, a qubit. Okay, what I mean by that is a quantum, not a binary bit, but a trinary bit. So I just invented this name. I don't know whether it is convention or not, but let's call it, let's say that my psi is belongs to a three-dimensional vector space. Okay, so it should look like this: a0 plus b1 plus c2. Okay, this is a v3 which belongs to a v3, a three-dimensional vector space whose basis elements are 0, 1 and 2. All right, so what I'm trying to say is that, let's say I have okay, let's do it here. So this is your 0 and 1 direction, and this is your 2 direction. All right, and let's say that I have a general vector, okay, not like this, somewhere here, okay, which is my psi. So I can obviously project it in this 0, 1 plane right here. Okay, rather than projecting it in a one vector direction, what we are doing is that we are taking the projection of this vector in this 0, 1 plane. Okay, and that is also a projection operator, and it follows all these properties that we were talking about. Okay, so what is the most general idea? The most general idea is that let's write it down, is that let's say we have this vector space V. Vector space V, and we want to decompose this vector space into these subspaces. All right, so let's say that we decompose it into V1, V2, V3 up till Vd. Okay, so let's pick one of them, and okay, let's pick one of them, and then let's call it E. Okay, then E is a subspace whose, let's say, whose basis is E1, E2. Okay, I think I should not call this Vd. Let's call it this something else, V capital D. Okay, you decompose it into D vectors, D subspaces, capital D subspaces, and let's say that this E space has small d number of elements. That means that this is a small d number of small d dimensional vector space. All right, so the definition is that if you want to project any vector in this subspace, then your pi e will just be e1 plus e2 plus up till ed. So how do you, this is the most general definition, so how do you connect it with the picture that we have here? Okay, so we have this big space V, which is V3. Let's say I want to decompose it into two vector spaces. One is this E, and this consists of this plane that we were talking about, which consists of 0 and 1. And there is another space, let's call that something else, E prime, and that is only consists of 2. All right, and if you take a combination of these two subspaces, you get the whole space again. All right, so what you want to do is that you want to take the projection in this E space. Then by definition, my projection operator pi e will be 0 0 plus 1 1. That is the definition that is given here. All right, let's check that. Let's check that I only get the projection in the 0 1 plane. All right, so let's check. I have this psi, which is equal to a0 plus b1 plus c2, and what I want to act on psi with e. Then what is this? This is 0 0 plus 1 1, and it will act on psi, so it will give me a0 plus b1 plus c2. All right, so if this is multiplied on all the numbers on this side, then this will only give me a non-zero number. This will give me a 0, this will give me a 0. So the only term will be surviving is this. A is a number, you have a 0, you have a 0 and a 0 here. All right, similarly, if you act upon these terms with this operator, what you get is just the second term, which is 1 1 and 1, and all the rest of the terms will give you 0, right, if you use the orthogonality property. And now you can see that this is equal to 1 and this is equal to 1. Then what it gives you is just a0 plus b1. This is what we were expecting. So we acted on psi, which is the most general one, with e, which is a projection in the 0 1 plane, and what we got is the 0 1 part only. So this is actually giving me the projection operator in the 0 1 plane. So this is projecting in the subspace E. So this is the most general idea. You can also check the properties, like pi e square is equal to pi e, and pi e prime, pi e is equal to 0, where e prime is some orthogonal subspace to E. All right, so these properties hold in general. So the main idea is that you just don't need to project in a one-dimensional subspace. You can project into a higher dimensional subspace as well, and these ideas hold in general. So these properties should be checked. Please should be checked by yourself. You will also use it in the assignments and the quizzes. So please make sure you understand them, and these ideas will be used in many applications of quantum computing. So please make sure you understand that. So one more thing I want to talk about is that this is something really important for the rest of the course, so we will try to talk about it. Let's say that X is a vector and A on V. So that what does it mean is that A is an operator or a matrix that acts on V, and it gives you a new vector X. All right, so if I take a dagger on both sides, which is a transpose conjugate dagger, and you have this A dagger, V dagger. Oh, sorry. I just want to take a dagger on both sides first. So AV dagger, then what does happen here? So you will get the bra of X, right? Similarly here you'll get V dagger, A dagger. I am doing it in the opposite order. Please try to focus, because if you have two matrices Mn and you take the dagger, then it will be in the opposite order. You can also check it for transpose. It's the same. All right, so it has to come in the opposite order. Now then V dagger should give me just V, and A will be given by A dagger. All right, so what it says is that so now if we have a number like this, A, M, B, we can think of it as M acting on B, which is giving me a new kit, and then you're taking an inner product with A, right? But similarly you can think of it as A acting on M, and then gives a kit B. So now if you take the conjugate of this thing, what you get is M dagger A. So when M is acting on the left, it is there is no dagger here, but when you think of it as a kit, then you have to do this transformation. But obviously it's true that if M is a Hermitian operator, then M dagger is equal to M. Then this you act on the left or act on the right, doesn't really matter. But whenever you are dealing with non-Hermitian operators, then you have to be careful with this equation. When it's acting on the right, it is just that operator, but when you think of it as something acting on the left, and you make a kit out of it, then you have to be careful with this dagger sign. All right, so that's all I wanted to teach you in this video. Thank you so much.